All right. Here we go. So last time we left off talking about forest succession, and we left off with this figure where we considered three different systems of different moisture status, and we talked about the different timelines for succession in these systems to a similar climactic climax stage in which the species that dominates the forest is the same species that is dominating reproduction in that forest, so you have the same species able to produce its young in the environment in which it has maximum biomass. What we want to do now is move into considering kind of the energetics and the large system properties of these ecosystems, which moves us into the field of ecosystem ecology. So far, a lot of what we've been talking about can fall under the umbrella of community ecology, or understanding how individual members of community change through time. Now we're going to transition into thinking about the properties of the entire ecosystem. This figure is a classic figure that was developed by Eugene P. Odom, but has also drawn on considerations of ecosystem properties that go back over 100 years before Odom produced this figure midway through the last century. So this figure in particular comes out of a 1969 paper by Odom that has been widely cited. It's what we call a citation classic. It's been cited thousands of times by other researchers, other papers. So in this figure, we have these letters denoting different processes in an ecosystem. And we have forest succession in the top panel, and then a microcosm succession in the bottom panel. And these were both considered by Odom. The microcosm was essentially a kind of a petri dish type system that Odom used to show that the same system properties present at a small scale would be present at a large scale in a forest. So a nice little demonstration. If you have a food jar in your system, in your refrigerator that you haven't tended to for a while, you might be able to watch succession of fungal species or something nefarious in there, and you could probably notice the same patterns if you were detailed in your observations. So let's get away from that analogy and just go to the forest succession panel on the very top. That's the important one that we understand. So the R here in this figure stands for respiration. And so through time, you see respiration increasing through time under the dotted line there. So that represents the amount of carbon that is leaving the system through plants respiring. This is because as plant biomass increases, of course, that biomass has to respire. Plants don't just bring in carbon dioxide, they also emit it, right? And they have to go through cellular processes just like other organisms, and carbon is the substrate that they use for their energy. So, of course, the plants themselves are respiring. They respire at a little faster rate generally when they are fast growing. And so you can see that the respiration rate early on in the system actually peaks. The respiration rate is actually higher than you'd expect given the biomass when the forest is relatively young. And then over time, the respiration kind of evens out as the forest is composed of less living material and more dead material stored in the center boles of trees, for example. We have two P sub n, the B obviously stands for biomass there. We have two P variables here to consider, P sub n and P sub g. We could rename these, and in the modern parlance, this would be NPP and GPP instead of PN and PG. So NPP is net primary productivity. Let's get to that in a second, and let's talk first about PG, or gross primary productivity. The best way to think about this, and we'll be talking about this a lot, is photosynthesis. This is essentially the amount of CO2 that the forest is pulling in from the atmosphere. So it's the gross amount of photosynthate that is fixed, that comes in from the atmosphere. Because plants also have to respire. They don't just bring in CO2, they don't just bring in carbon, they also have to respire carbon back out. The difference between gross photosynthesis, or the gross amount of carbon that is sequestered by the plants, and respiration is what we call net primary productivity, or in this figure, P sub n. It's the net amount of carbon that is actually fixed into usable biomass, or visible biomass, essentially what's left over from photosynthate after respiration has taken place. And so the shaded area represents essentially the visible annual increase in green material. If these graphs were perfectly matched, you would probably see the steepest point of the biomass curve would match up with the largest amount of net primary productivity, or the thickest part of the gray area there, because of the way that these are related to each other. Okay, so as a forest proceeds through succession, we expect biomass to increase. That's a given. As that biomass increases, we expect respiration to increase. And because there's variation in the rate at which biomass increases due to young trees being generally fast growing, and differences in how much respiration a given amount of biomass undergoes, depending on the nature of that biomass, whether it's old or young material, we get some variation in the actual rate at which carbon is brought into the system and then fixed into permanent material. Permanent vegetative material. But in general, this theory of how biomass, how carbon has changed over time in forests has gone relatively unchanged for going on 100 years. So around that amount of time, we've kind of considered that this should be what we expect for a forest ecosystem. Now, the timeline here is obviously flexible, and it depends on the system we're working in. Just like in the last figure, we were talking about forest succession that might last 10,000 years versus forest succession that might last 100 years. The timeline here is similarly flexible. What Odom showed in a microcosm, and what we can also demonstrate through chronosequences, at least in forest succession, is that it seems that as biomass reaches a peak, and as a system gets really, really old and reaches that kind of climax condition, there's a hypothesis that a biomass will level off as the amount of gross photosynthate starts to equal the amount of photosynthesis starts to equal the amount of respiration. So in other words, GPP and respiration come into balance. When they do, the net primary productivity of the system, we would expect, would actually go close to zero, or at least it fluctuates around positive and negative range, which you can see here in Odom's microcosm. So this, in the 1960s, was very fitting with the idea of kind of undisturbed nature and balance. If you let a system reach its ultimate stage in succession, biomass levels off, respiration equals photosynthate. So inputs equal outputs, and everything is in balance and in stasis. Of course, we know that's not really the case, and more recent research has really shown us that our old growth systems that we previously thought were stable, in fact, are still accumulating carbon at a relatively fast rate, and we can't really make this generalization very well. It may work on average in many systems, but we certainly can't apply it to all systems, and certainly not everything that we call old growth will fit this bill. Other elements, if we go beyond carbon, so what we were just talking about is photosynthesis. If we move into something like phosphorus, you get a completely different pattern in the through time dynamics. So for example, phosphorus, we know that phosphorus, the ultimate source of phosphorus for most ecosystems, comes from rock. And so we start out with mineral phosphorus that weathers out of rock. This phosphorus can have a number of fates before it's biologically available. It can be taken up and turned into organic phosphorus, but can also be occluded and essentially locked out of circulation biologically. But regardless, the amount of phosphorus in a system can be graphed with reference to the age of the system. And there have been a number of important studies, especially in tropical locations. Hawaii, there's a classic system in Hawaii that's been used for this, where islands are different ages. And based on the different ages of those islands, you can develop a chronosequence and look at the phosphorus availability in the system. And what you find is through time, phosphorus just generally declines. So phosphorus doesn't have a strong atmospheric component to its cycle. There are some interesting studies where you get phosphorus transfer through dust from desert regions to more temperate regions or more tropical forests. But in general, in most systems, phosphorus is on the decline over the long term. It gets weathered out of the system and generally disappears through stream water, through erosion. And so that ultimate source, that ultimate rock source is where you start, and then you're only going downhill. Because of this, really old forests tend to be phosphorus limited, and that's been observed for a number of years. Whereas younger systems that are volcanically younger, tend to be less phosphorus limited, and they tend to be more phosphorus rich. So phosphorus through time tends to just decline. So we can talk about all elements in this context. You can go through one at a time of all the kind of biologically important elements and look at their cycles, and they don't always map each other. So sometimes they can have a little bit different pattern in how they change through time. When we start thinking about forest management, we have other dynamics that we have to think about. And so forest management in the form of clear cutting or harvesting has effects that may be surprising in terms of their effect on element cycles. This is a classic figure, first demonstrated by Covington in 1974. The black dots represent data from Covington, and then the white triangles represent more recent data, trying to evaluate what we call the Covington curve. And the Covington curve essentially refers to the amount of organic mass that's left in soils following a clear cut in a forest floor. So in this case, you go through and you harvest a forest floor, and then you measure the amount of carbon that's present in that forest floor through time. And what you find is following a clear cut, following removal of the forest, you have this open environment. It may be a little counterintuitive, but it can actually be a little moister in many situations because there's less rainfall intercepted by the above ground vegetation. So you have this wet, moist, warm forest floor. And what does that do to respiration? It just throws it through the roof. And so you have decomposition of a lot of fine particulate matter that's left over from the clear cut. And you start out with this thick forest floor, and over time, you can watch it shrink in a clear cut. And so you're actually losing carbon to the atmosphere as that material on the forest floor degrades. However, over time, say 20 years in, you start to accumulate enough biomass that the new forest growth starts contributing to that forest floor again. And so over time, the amount of carbon in that forest floor again increases. And as that increases, we get an increase in forest floor till eventually we again reach a stasis where we're expecting the rate of decomposition of that material is coming close to the rate that material is being added to the forest floor. So because of this, eventually, once the forest is mature, we expect that the thickness of that organic matter layer levels off. Associated with this, you might expect that you could see, if you were not just measuring the depth of the forest floor, and instead you were measuring the rate of evolution of CO2 or respiration of CO2 from the forest floor, you would see a peak in respiration at a time at which the forest floor here is declining the sharpest. And so the red line here might represent what we call net soil CO2 efflux, or the rate at which CO2 is leaving the system from the forest floor. And this has been tested by numerous researchers, including Dr. Ruth Yanai here in a paper in 2003, in which they went through and evaluated the amount of organic matter left over after clear cuts and evaluated this kind of Covington curve idea and the soil carbon dynamics associated with it. You can measure soil CO2 in a number of ways. Typically, there's a soda lime method that people will use where they place soda lime in a chamber. Soda lime will capture the CO2 as it evolves out of the soil, and based on weight, you can measure the amount of CO2 that evolves over time. Or you can use a little instrument that in real time here captures the CO2 as it comes out of the soil and then measures the CO2 content of the air, and through that can calculate the rate of CO2 evolution. And we've done both of these methods in my lab and in classes like the one you're taking now. So, if anything, what these slides should really demonstrate to you is the importance of recognizing that carbon is not just something like carbon or something like phosphorus. These elements, understanding them in ecosystems requires that we not just think about how much, but we have to think about the rates of inputs and the rates of outputs. So wait for it, it's about to get exciting. Here we go. We're talking about pools and fluxes. Okay? I don't. You waited all the way until the 17th minute of this video just to see that animation, and you're welcome. So let's talk about pools and fluxes. So this is a volcanic pumice plain. This is on Mount St. Helens. And we have a system that has essentially been reset. We have vegetation that's just increasing gradually through time. A young forest might look something like this. We have young, sun-loving plants that come in, like Douglas fir. They dominate in high densities. You have high densities of individual trees dominating on a forest floor. The rate of increase in biomass is very fast. These trees age, and as they age, they change in their structure, they change in their form, they change in their density, and the rate of input may or may not actually slow down as these trees become older and as the forest becomes older. But the amount of material that's there has increased dramatically. So where we started with no biomass, we gradually increased our biomass until we have maximum biomass, even if the rate of input of new biomass is slower. We can think about this in terms of three globally important acronyms related to carbon cycling. GPP. GPP is essentially the rate of photosynthesis. It is the amount of carbon that is brought into the plant, period. The amount of carbon that is fixed through photosynthesis. NPP is the amount of carbon that is left over after the plant has fed itself, after it's gone through respiration itself. Plants have to release carbon too, and there's an amount of net vegetation that's left over after respiration has been accounted for. Then there's an acronym we haven't talked about yet, and that's NEP. NEP is net ecosystem productivity. Plants respire. Plants fix CO2 and they respire. But what we were just talking about with Ruth Yanai's research and the Covington curve related not just to the plants themselves respiring, but dead material that is respired by microorganisms and fungi in the system. And so the soil is also essentially respiring. It is releasing CO2. What we'd really say is the organisms that live in the soil, or the heterotrophic organisms in the system, are also respiring. So we have autotrophic respiration, which is what gave us NPP from GPP. But then we have heterotrophic respiration, and we have to subtract that from GPP2 before we can get NEP, net ecosystem productivity. These three acronyms are probably the most important acronyms to learn if you want to understand carbon cycling in forests. Once you've kind of understood those, then a lot of the rest of the carbon world becomes a lot easier to understand. So this was a longitudinal study, but we don't really know in Odom's work whether, this was a chronosequence approach, rather, excuse me. But we don't really know whether these patterns hold out in a longitudinal study. So a longitudinal study is a study where you've actually watched the same ecosystem through time to see what it does. versus a chronosequence study, which we've talked about, which is a space for time substitution. So let's talk about watching ecosystems and our methods for doing that over time in a longitudinal framework. We have so many tools at our disposal now that we didn't have 100 years ago, that we didn't have 50 years ago. And one of the most impressive new tools that is really advancing ecosystem science is our ability to use spatial information or information from satellites to detect things like ecosystem carbon uptake. Here in this graph, we've got most of the Pacific Northwest, the United States Pacific Northwest, represented in a map, and the varying shades of green refer to what we call normalized difference in vegetation index. This is from a 2008 satellite data in July of 2008. You can find through online GIS portals that readily available data on NDVI for any period in recent history that you're interested in for the Western United States. You can find it for this year, you can find it for last year. It's readily available, and hopefully you get a chance to explore that soon. Essentially, NDVI tells you a greenness index. It tells you about the amount of light that is taken up by green vegetation in a region. And so that's a really important variable because it's directly related to leaf area. It's also directly related to the amount of carbon that a system can take up. So, for example, in these graphs here, we have NDVI on the top two graphs here. We have NDVI as an x-axis predicting NPP and GPP. And while for analytical chemistry, the relationship between those dots in that line might not be perfect, for evaluating patterns at a global scale or a widespread landscape scale where all sorts of things affect the productivity of vegetation, being able to just simply take satellite images and predict the GPP or NPP as tightly as you can see in these curves is a little bit of a hat trick. It's a pretty impressive feat. And so we get pretty good predictability of the amount of carbon that's coming into a system through GPP and the amount of carbon that's left over as green material, NPP, just through using satellite images of NDVI. And through this, we can make estimates of things like the amount of net primary productivity that's taking place over wide regions. So maybe we only have 80% predictability of this, but it's information we didn't necessarily have before, and it's accurate within 80%. That's pretty good. And sometimes this is just showing us pretty intuitive patterns, but we can get an actual value on our NPP. So we can actually quantify the amount of carbon that is left over as green material. So as you can see here in the Pacific Northwest, west of the Cascades, you see much darker values. As you get down into Northern California in the Redwood Zone, you see extremely dark values. On the west side of the Olympic Peninsula, you see darker values. These are places where NPP, or carbon gain and storage, is highest. These are some of our most carbon dense forests, but they're also some of our most productive forests on the planet. So we have really high values of NPP. So this is one way we can get at it, through some satellite data. Other ways to get at this include really simple methods. So let's go all the way to the other end. We started with high-tech methods associated with satellite acquisition of reflectance data, and then using some kind of statistical hat tricks to turn that reflectance data into estimates of carbon gain. But what about just isolating individual points on a forest floor, individual locations in a forest, and then tracking the amount of carbon, inventorying the amount of carbon through time in one location? Well, this has been the goal of our Evergreen Ecological Observation Network, something that many students at Evergreen have gotten a chance to participate in. In this project, we identified 44 individual plots randomly. We had a random start and a grid network for locating some plots. And we used those plots to track changes in carbon through time. We do periodic carbon inventory. Mostly it's every 2 years. Sometimes it's more frequent than that. The plots are 10 meters in diameter, size that was matched to the size of forests that we have, the size of trees and their spacing. We have a series of plots that are measured more intensively, but the key thing is that we go through and inventory the amount of biomass in these forests on a regular basis, as you'll be doing in your own plots. So when you're assigned a plot, you'll be going to it and inventorying the amount of carbon in that plot. That will be matched with the amount of carbon that we have, that we know has been in those plots since 2006, in many cases, 2007 in some other cases. We also have done detailed net soil CO2 efflux measurements in these plots, so we know the rate of soil evolution of CO2. And we've done that using the two methods I described before, one in which we use soda lime in open containers and then in a chamber that clamps over the top, a really simple method based on weight differences. And then we've also used instruments that directly measure the amount of CO2. Commonly, when you have forest inventory data or you have data on the size of trees, you can convert that to the amount of carbon in a forest based on taking each individual tree and applying what we call a biomass estimation equation to that tree. So a biomass estimation equation uses known biomass from trees that in the past had been harvested and weighed, and the known dimensions of those trees to estimate the biomass through regression analysis. So in this case, I have an equation for Douglas fir or Pseudotsuga menziesii above ground biomass. We estimate that approximately 50% of the mass of a tree is carbon. So if we can estimate the amount of biomass using this equation, then we can also estimate the carbon. It turns out the amount of carbon, 50%, is probably a little bit of an overestimate. It's probably more like 42 to 48%. But for our purposes, 50% is a global assumption that has been used by a number of different studies, and we'll stick with that even though we know it may be a little bit of an overestimate right now. If we come back from, if we do this inventory at time 1 and we come back and do the same at time 2, then the difference over time we can use as carbon gain for a given forest. We can do the same for snags and down logs. So essentially, the beauty of this approach is that we can use simple measurements out in the field using tapes that we wrap around trees, using tapes that we drag along logs. We can use simple hands-on methods, and from that, we can estimate the amount of carbon in a system. Here's an example. This is data that I put together way back in 2008. We could do the same for this year, where I used some data in some other plots that you'll get to work in that are at Evergreen and date back to 1975 or 1977. In this case, you can see this is the megagrams or tons of carbon per hectare that are in our forest, estimated to be in our forest, plus or minus standard error, I believe, through time. And so in 1977, our forest might have had around 160, 170 tons of carbon per hectare. By 2008, our forest had leveled off somewhere closer to 260, 270 tons of carbon per hectare. And then we can see what they are this year and see if we're still in a leveling phase or are we at the exponential end of the curve. Understanding that change through time is really important. There have been a number of controversial, and I'll end with this, there have been a number of controversial approaches to thinking about carbon sequestration in forests associated with the age of those forests. From the timber industry, we've heard over and over again the argument that young forests are more productive. Therefore, if young forests are pulling in carbon at a faster rate, then we should liquidate all those old geriatric forests that are no longer bringing in carbon quickly and replace them with young, vigorous forests that are bringing in lots of carbon. And this is really a misnomer. It's a misnomer there are several data sets in which you can see that the NPP, or the rate of carbon fixation into new green biomass, can be much higher at younger stands. This is true for Douglas fir, and it's true for species all throughout the temperate forests of North America. You can find stands in which this is the case. However, The relative age here is going to be different in different systems. So one point is that it's possible that for a forest like a Douglas fir forest, you might not reach this peak until your forest is around 200 years old. Well, the standard rotation in Pacific Northwest forestry is much younger than that. Forests are typically cut between 40 and 80 years old when they're on a standard replanting and cutting rotation. So in that case, this figure would lead you to believe that peak productivity occurs around 60 years, 60 to 80 years. It would justify our rotation length in the Pacific Northwest, but it might not apply well to many forests of our region. Secondly, NPP isn't everything. Remember, there's a lot of carbon that's stored in these forests. So even if they have slowed down in the amount of carbon that they're bringing in, they're still major carbon stores. And remember the Covington curve, if you cut those forests, we're going to release a lot of that carbon back to the atmosphere from the soils, whether we intended to or not. It doesn't matter if you take the wood from those trees and build them into houses, a lot of the carbon in the forest is going to be lost relatively quickly. This has been modeled multiple times, and Mark Harmon, a researcher at Oregon State University, has really led this work. There are a number of other researchers, including Beverly Law and Barbara Bond, who've really led research on understanding how carbon changes through time in Pacific Northwest forests and in relation to fire and other disturbance events. And generally, and all three of those individuals are down at Oregon State University. So this is an older paper, but it's one of the first papers in which Harmon really clearly laid out for people our expectations with regard to carbon dynamics through time. So, for example, if we talk about wildfire or harvested forests, just like we saw in the Covington curve, we have an expectation that through time, the percentage of old growth carbon storage following that disturbance is going to decline. So it doesn't matter if we're talking about a wildfire or a clear cut, we're going to lose carbon in that system following the cut, not just due to tree removal, but due to increased respiration from the soils and loss of organic material that's left over. We should anticipate from a normal set of not radical, but just basic assumptions that a harvested forest is going to lose more carbon than a fire-affected forest. This is because fire doesn't kill all trees. It also tends to remove the finer materials, but it leaves behind a lot of larger material, large stumps and large snags. Through time, that forest might recover to its previous amount of carbon storage. So on the y-axis here, we have the percent of original carbon that has been removed and then increases through time. And so our assumptions for this model will vary depending on if we assume there's an increase in decay rate, or if we say, oh, that's unrealistic. I think my forests, after they're cut or disturbed, there's no change in decay rate of the material. Well, it doesn't matter. Either way, we get a decline and then a rebound. And we get less of a decline in wildfire and more of a decline in a harvested forest. If we look at a forest that is reharvested at intervals over and over and over again, we can think about that forest in terms of leaving material slashed and distributed on the system, residues left. We can think about 45% of the wood is pulled out and stored in building material. It turns out that's actually that's a good estimate over time, especially when we're talking about hundreds of years. A lot of material is lost in sawdust or in materials that like paper that generally don't last very long before they decay. And we can have situations where all residues are removed from the system. And what we find is regardless, you get this kind of seesaw pattern that happens in carbon where systems will start to recover the carbon that they had prior to harvest, and then it gets removed again. They start to recover and then the carbon gets removed again. And this happens over and over again. As you can see, if we assume that a good amount of the wood ends up in long-term storage and the residues are left over time, say in this case over 350 years, we start to occasionally, at the peak of that forest rotation, get close to 80% of the original old growth storage. So we can get back to around 80% of what used to be in the forest from old growth. But regardless, we have a 20% loss in the total amount of carbon. So we have a little bit of a carbon debt from a previously old growth forest that was cut, even after 350 years of intense rotation. Um, Asking if you can cut a forest and have more carbon left over in the forest is akin to saying, can I spend more money and have more left over in the bank? Well, it doesn't quite, those aren't perfect analogies, but it helps you get your head around the idea that no, if you're continually removing material from the forest, it's very hard to have more carbon left over in the forest than you started with. Other management scenarios would have the carbon over time in the system degrade considerably. And so you might be left with only 50% of the original carbon, even after 350 years. And in fact, the amount of carbon at peak rotation age might actually decline through time if you continually remove your residues. Based on this, I'll let you read this on your own time. You can pause the video and read this. But based on this, Harman and others now have calculated carbon debts. And so this helps us understand that, you know, our carbon storage might have been reduced by something like 300 tons per hectare by the conversion of old growth forests to young forests in our region. A tremendous amount of reduction. And so that accounts for a lot of the carbon dioxide that is in the air, as it turns out. So a lot of our carbon dioxide that we're currently dealing with in a global change scenario can be accounted for by the loss of CO2 associated with cutting old growth forests and releasing that carbon into the atmosphere. So I'm going to end it there, and let's end with this photo, which is a photo of a wildfire affected stand. In this case, it's a pine stand. It demonstrates several principles that we've just covered in this lecture related to community composition, high densities of small trees coming in, sun-loving small trees coming in following a major disturbance. And it demonstrates that many disturbances, such as fire, which can be a good thing to be reminded of following a big fire season, don't completely remove the carbon from a system. Here you can see the remnant carbon in this system represented by remnant standing trees, even in this high severity wildfire situation. And let's leave it there. This has been a long one. Thanks for hanging in, and that's it for today's lecture.